Some problems are more challenging than others. If you can identify the appropriate u off the bat, then that's most of the battle. So in the case of number 5, yeah, there's a lot of things that u could be, but the idea should always be that whatever you select as u should differentiate to help you cancel out the other part of the integral. So basically, whatever u is should have a derivative that's pretty close to the other part of the integral. All right, so my choices here are tangent, secant, or secant squared, or some other combination of the things. When you're dealing with trig, another possibility could be to convert it over into sines and cosines and see where that takes you. But if you just kind of play it out, you'd say, all right, well, let's say I think it's secant. The derivative of secant is secant times tangent. Maybe that'll get the job done. But there's a better one. That would be the case where u is equal to tangent, because the derivative of tangent is what? Secant squared, aka the thing we want to get rid of. So du equals secant squared x dx, and that's a clean substitution. All right here, secant squared x dx, we can replace that with a u. On the bottom we have a tan x, which is going to get replaced with just a u. So we're looking at really du over a u. You could rewrite that as the integral of 1 over u du. Antiderivative of 1 over u is what? Ln of u plus c. And we have u specifically as the tangent of x, so now we have our integral, the natural log of the absolute value of tangent x plus c. Oh, that's part of the rule. All right, so for number 6, it solved the differential equation, which means we have to get it in the appropriate form first. So I'm going to do a little housekeeping. So dy equals x minus 4 over the square root of that lovely quadratic. Dx, we're integrating both sides. But really it's the antiderivative on the left-hand side, antiderivative of 1 dy. There's the understood 1 there. The antiderivative of 1 with respect to y would just be y. So y equals this integral. That's all just setup work, though, because we haven't even gotten to the part where we're actually integrating. All right, so we want to select an appropriate u, and really it's just a matter of deciding again which part, when differentiated, will allow us to cancel out the other part. So I think it's obvious that I wouldn't want to select x minus 4, because if I take the derivative of that, that's going to give me a 1. That's not going to cancel out anything. If I take the entire radical, that's going to be a messy chain rule. That's overkill. All right. We need a fly swatter, not a sledgehammer here. So I'm going to let u be just the x squared minus 8x plus 1. And then I'll differentiate that. All right, so du is equal to 2x minus 8 dx. All right, and that's great because that's a constant multiple of x minus 4. It's exactly double it. All right, so chop this in half. We'll be looking at 1/2 du is equal to x minus 4 dx. That's the thing we want to get rid of. Well, one of the things we want to get rid of. So I'd be looking at y equals the integral of 1/2 du over the square root of just the u. All right, we'll clean that up a little bit. Definitely much simpler than what we started with, and that's the objective here. We're looking at 1/2 u to the negative 1/2 du. We integrate that, and what do we get?
to the 1.
Just u to the 1/2, right? Plus c. Yeah, because the 1/2 divided by the 1/2 will cancel. If it was 1/2 divided by 2, then it'd become 1/4. Right? So quadratic will replace the u, so x squared minus 8x plus 1 to the 1/2 power plus c. All right, so again, all that u sub work is just to get it from the messy form into something that's reverse power ruleable, I guess. So mission accomplished. That's the idea. The only extension to this really is the concept of initial conditions. So actually finding out the value of c. These are obviously the difficulty level is dependent on the nature of the function. If you're dealing with something that's out of your wheelhouse in terms of coming up with derivatives, then it could be a little crunchy. But the process itself is the same. Right? So it's you're grounded in familiarity, which is a good thing. All right. So number 7. Kind of like a little baby u sub action, because you could actually come up with the antiderivative of this without using u substitution. You can do a little trial and error. Just because it's secant squared, it's going to be tangent of something that has a derivative equal to secant squared. It's just a matter of what the something is. All right, but we'll play it out with the complete approach. We'll use u sub, even though you could streamline it. So f prime of x is the same as saying d f of x dx. In differential form, it's d f of x equals secant squared of 2x dx, at which point we integrate both sides. So this is just notation, really, more than anything else. Okay, because we haven't even gotten to the u sub yet. Okay. So the antiderivative of a derivative, inverse operations cancel each other out. So on the left-hand side, it's just f of x. Right-hand side, secant squared 2x dx. All right. A lot of times, I think when I think of u sub, I think it's kind of weird. In my mind, I call it the if-only method. Like, if only this were secant squared, then I would be able to find the antiderivative of it. Right? So, if that's the case, then the thing I would want to change would be the 2x. Sometimes it's pretty clear to see the thing that you would want to make the u, right? Because if only this were secant squared of anything other than 2x, just an x instead of a 2x. Right? If it were tangent of x squared minus 30, I would want it to be tangent because tangent's cleaner. We have rules for that, although we haven't covered that rule yet because we haven't learned integration by parts, but there is a rule for tangent. If it were 1 over something elaborate, I would just want it to be 1 over u because I know the antiderivative of that would be the natural log. Right? So if only it were the parent function. So define u as the thing that would make it a parent function. Right? In this case, we're looking at du equals 2 dx. All right, and so I don't have a 2 dx in my integral. I just have the secant squared and a dx. So let's clean this up and make it 1/2 du equals dx. And so that would be my substitution. So this would become the antiderivative of secant squared u times 1/2 du, rewritten as 1/2 secant squared u du, which anti-differentiates to 1/2 tangent u plus c. That's my f of x. All right. Now, it is f of x, so the u has to get swapped out for what it truly is, so I'll make that adjustment in a second. And we're also given an initial condition, or we're given a condition. So we'll have to flesh out what the value of c is. So f of x as a general solution to the differential equation would be 1/2 tangent 2x plus c. So this is a general solution. All right, the initial, or the condition that was given is pi over 2 comma 2. So f of pi over 2 would swap out the x for a pi over 2, and the result should be equal to 2. All right. So this is going to be tangent of pi, because 2 times pi over 2 is pi, right? So what is the tangent of pi? Zero.
Oh.
You totally had it. Yeah, tangent 0 wherever sine is equal to 0. So if you know that you're looking on the x-axis for where sine is equal to 0, then you have it. Okay, so cotangent would be equal to 0 wherever cosine is equal to 0, which would be on the y-axis. Okay, so I have my c value of 2. So my particular solution, f of x equals 1/2 tangent 2x plus 2. And this is the particular solution. You could have also actually, with conditions, it's kind of cool. You could work with it in u form. It's just you'd have to redefine it as f of u. But you could actually figure out what the u would be corresponding to the x value that's given, because u is equal to 2x. So if you knew that x was equal to pi over 2, and u is twice that, then you know that u has to be equal to pi. You can just plug it in that form.
In the step above the general solution, you go from tan u to tan 2x, but then f of x stays the same, wouldn't it? Like, if you're substituting u for x, wouldn't it would have to be f of 2x?
Well, I'm only reverse substituting. I'm replacing the u with what it truly is equivalent to. I'm not doing a composite function. So, similar idea, but different action. All right, and the last one. Actually, I have no idea what time it is, so maybe we're already done. Oh, we still have time. All right, so same idea in terms of the setup, but at least, in terms of, or in the interest of brevity, we can just kind of hop to the step where it's f of x equals, because we know it's going to amount to an integral anyway. So f of x equals the antiderivative of negative 2x. I'm going to write it as 8 minus x squared to the 1/2 power dx. Right. The inner function here, 8 minus x squared, very nice inner function, because its derivative is the coefficient function, the negative 2x. So I would want that to be equal to 8 minus x squared, making du equal to negative 2x dx. And so that would be a clean substitution. Be looking at u to the 1/2 du. All right, nice and clean. The antiderivative of which would be exactamundo plus c. Right, and so that would be what f of x is equal to. If we reverse substitute, it'll be directly that. Oh, glitchy. So that's my f of x, and I just have to figure out what c is. I'm given the condition that f of 2 is equal to 7, so f of 2 is equal to 2/3 8 minus 4 to the 3/2 plus c equals 7. 8 minus 4 is 4 to the 3/2 power is what? 8, right? So 8 times 2/3 is going to be 16/3. Just a common denominator on the fly there. So C would be 5/3. So our particular solution, f of x, would be equal to 2/3 8 minus x squared to the 3/2 plus 5/3.